So, coming to the fourth video of this module, the moment of inertia of composite areas. So, till now we have studied a regular plane area like either rectangle, triangle, semicircle, etc. Now we are going to find the moment of inertia for the composite areas like we did for the centroid calculation for the composite areas. So here, the composite area can be divided into a set of simple areas. Moment of inertia of each area about its centroidal axis can be calculated. Using the parallel axis theorem, the moment of inertia of each area can be calculated about the required axis. Summing up of the moment of inertia of the each simple area gives the moment of inertia of the composite area. So for this composite area, we need the parallel axis theorem. It's very important because each area will have its own centroidal moment of inertia. We need to actually shift the individual centroidal moment of inertia to a defined or base axis by the ig plus ax square equation. Okay, so question is to find the moment of inertia of an unequal triangle, sorry, unequal angle iron section of 250 mm by 20 mm about its centroidal axis. So this is a little bit tricky. Tricky in the sense we want to find the moment of inertia of this section about the centroidal axis of the entire section, right? So we directly know the equations of centroidal axis, centroid moment of inertia of individual rectangle, say 1 and 2. Okay, so we have first rectangle here of 125 by 20 and second rectangle 230 by 20 and area 1 125 into 20 2500 A2 230 into 20 4600 x1 x1 means it is the uh, horizontal value, right? So x1 means for area 1 the x1 is centroid of this rectangle 125 by 2, so 62.5. For x2 20 by 2 10. Y1 in the vertical axis for the area 1 20 by 2 10, and for the second area it is 20 plus 230 by 2, as we're taking all with respect to the base reference axis. Yeah, so please don't confuse with this x and y. These are the not imaginary, but these are the real centroidal axis. But we are actually calculating all these values with respect to the this axis from here left and from here top. So we can apply directly the equations to find the x bar and y bar which you have laid, and you got will get the value as 28.48 as x bar and y bar as 90.9 and 28.5 and 91 approximately. So from this axis 28.5 and from here 91. So you got the x bar and y bar. Now coming to the calculation of moment of inertia, these are the explanations of x bar and y bar. You know this equation a1 x1 plus a2 x2 by a1 plus a2. Similar for the y bar calculation. We have ig ixs or ig1 xs, that is moment of inertia of the first area with respect to centroidal axis of this particular area, which is the BDQ by 12. We have learned this formula previous. So B is 125 into 20 cube depth by 12 will give you this much higher value. And for independently for the second area with respect to its own centroidal axis, it is 1 by 12 into 20 BD cube. So 20 is the width, depth is 230. So this heavy value. And similarly for the different axis, that is we what we found is with respect to x-axis. Similarly for the y, please recollect that only that BD cube by 12 only B and D will interchange, right? So this 20 into 125 cube, and for second one 230 into 20 cube. Those changes are there, and we found the moment of inertia with respect to the centroidal axis for both the individual areas. Now we need to shift the centroidal moment of inertia to the actual centroid of the entire cross section. Right. We clearly know the location of centroid is this x dotted x line and y line, and IGXX, this is moment of inertia of the entire uh, section with respect to the horizontal axis is equal to IG1XX first area plus A1 square. So this first bracket term is for the first area and second one is for the second area. Right. So like this is for the individual centroid moment of inertia for the first area. This is individual centroidal moment of inertia for the second area. A1 square is this is actually the parallel axis theorem of shifting or finding the moment of inertia about any baseline, provided h is the distance between centroid to the centroid of total figure to the centroid of the figure to the baseline considered. Right. So here the baseline considered is the centroid of the total section, which is shown as this total line. H1 is equal to y bar minus y1. So for the first one, this one, we know that from bottom 91 is the centroidal axis of the entire figure. 91 minus this 20 by 2. So between G1 value is 81. H value, H1 value. H2 is we have Y2. Y2 is given by 135. How come? That is 115 up to centroid 230 by 115 plus 20. 135 minus 91. Please note that the sign doesn't matter as the term will be squared. So whatever if you take like above or below, only the distance matters, not the sign. On squaring, it will be cancelled off. So you can directly apply the equation to find the IGXS. So you got the values. We'll repeat similarly for the IYY axis also. Right, I'm not repeating those things. Calculate the moment of inertia of the area shown in figure. Here 150 is the width, total depth 300, 20, 20. So first thing to come into your mind is that you have to divide this into the single independent areas. So the number of areas, whether you want to divide this into 2 area, 3 area, 4 area, whatever it is, it entirely depends on you. Whatever number of areas you take, make sure that you're taking in the right way. So in this solution, they have taken as 1, 2, and 3, and this is the first area, second area, third area. So area 1 will be 130 by 20, 2 will be 300 by 20, 3 will be same as the 130 by 20. There will be a easiness in this problem. I'll explain that. Okay, so G1 is the centroidal axis of the first area alone, G2 for the second area, G3 is for the third area, G is the actually the centroid of the total area. Okay, yeah. So we can find the area A1, A2, A3, all are known to you. X1 means the horizontal way, right? So considering this, 20 plus 130 by 2. So 20 plus 65, 85. x2 half of this area, that is 20 by 2, 10. X3 is same as of x1, or taking with respect to this y axis, 85. Y1 similarly for, so y1 is the vertical one, right? So for the y1, we're taking with respect to this axis, okay? Y1, uh, okay, there's a small difference. Small difference is that we are not considering about the base. We are considering this directly on the this shown axis xx. So whatever the case, the x won't change as the x is taken right side. There is no issue with that. In the case of y, we have to take with respect to this axis, x's axis. In that case, y1 is 140. How come? From here, total is 300. 300 by 2 will be 150 up to this point minus this half. So because from here, please see the cursor, from here to, or from G to G3 is the value of y1, and G to G1 is the value of y3, and y2 is on the centroid of this second area is on the line of xx. So there is no change in the or there is no value for that. Please note that there should be a sign change. X bar 44.821. So from this point at a distance of 44.821, at this point the centroid of the entire section G, entire section lies. Due to symmetry, y bar is equal to is on the same line. So, so our new axis will be this. And now there is a positive thing for us. The positive thing is that on the calculation of, okay, I'll explain my well, the problem is on IGYY. IGYY, it is the moment of inertia with respect to the YY axis. Okay, so we are taking we're taking sorry taking this axis, passing through the G vertically and horizontally, and IGYY is equal to IG1YY. IG1 is this area. For this rectangle area alone, the value is half 1 by 12 into 20 into 130 cube. Please note that this actually half 1 by 12 into BD cube. B is 20, D is 130. So this is that explanation for this one. Plus 130 into 20 is the area of A1 into 40. So how come 40? So 40 is the difference. So it is actually 40.179, right? That is 40.179. This value is the distance between G1 and G2. That is, we have the G1 value as 20 plus 130 by 2. It is 65 plus 20, 85 minus G is 44.821 will give you the 40.179, and so we got the corresponding shifted moment of inertia of area 1 with respect to centroidal axis. Similarly for the area 2, we have yeah, for the area 2 we have 1 by 12 into, so the base will be this long one, 300 into d cube. 20 cube is for the individual or the individual centroidal moment of inertia, plus a x square. 20 into 300 is the area of 2 into g minus g2. That is actually 44.821 minus 10. So 34.821 plus 1 by 12 into 4. Actually, for G3, it is same for the G1 because all are at the same distance and have same area with respect to the base. So it is again the repeat of first one, 1 by 12 into 20 into 130 cube plus 130 into 20 into 40.17 square. We got the value. Alright. And yeah, the IG excess also can be calculated similar to the previous one, but here they did it in a different way. The different way is done uh, accounting the similarity. That is, if you consider a rectangle on this place, say I'll just draw that option 10. Yeah, please consider this as a rectangle. Yeah, sorry, rectangle. And please note that this real composite figure as well as this rectangle both have the centroid same, right? Both have centroid same with respect to the x-axis. Y it will change, x-axis both are same. So we can, what we can do, we can actually find the centroid moment of inertia of the entire cross section minus, so like big one that is considering the uh, yeah, you can I'm just doing it in a blue pattern. Yeah, you can subtract the centroid moment of inertia of this red triangle from the blue triangle to obtain the centroidal moment of inertia of the given section. That is executed here. IGXS is equal to BDQ by 12 minus BDQ by 12. Uh, so B and D are for the big one and small b and d for the small rectangle. Hence the values B is equal to 130 plus 20, D is equal to 300, B 130, D is equal to 300 minus 40. So IG access for the big rectangle is this much high. No, sorry, the first portion 112 1 by 12 into 150 is the base width into d cube 300 cube minus 1 by 12 into 130 into 260 is the depth of this small rectangle, will give you directly the IGXS value. So this give you an idea that you could even perform the moment of inertia calculation when there is a symmetry advantage in a easier way. Yeah, for this problem which is displayed on the screen also, we can use some symmetry advantage. And I section has the following dimensions. Just a minute. So in this problem, an I section having a section shape like I has the following dimensions: top and bottom. Maximize this. Okay. Having top and bottom flange width 120 flanges. These are the flanges 1 and 2, and this is the web portion. The flange width is 120 mm. Depth of web is 180 from here to here. Thickness of web, this value is 10 mm, and both flange also. So for this is 10, this is 10. So all thickness are 10. 120 is flange width, 180 is depth of web. Sketch the section and determine the area moment of inertia about centroidal axis y. So it's actually easy in the sense these are symmetrical with respect to the x axis as well as the y axis. Right, the centroid will pass through pointer pen, maybe approximately through exactly through the center and through the center. So this is actually beneficial, uh, so that we can pointer in color I can take as maybe green. So you can consider one area like this. Maybe it will be shown in this one. Okay, let's see how it is solved. There are multiple ways of solving this. In this particular solution, actually, the section is symmetrical with respect to the centroidal axis and y axis. Right. So, so the section is symmetrical with respect to centroidal axis and y axis since G1, G2, G3 and G are on the same y axis. So centroidal y will pass through this line, center point, and for all the um, no, actually this G1, G2, and G3. Yeah. So please note that centroidal axis of uh, this one will be like this. So please note that the centroidal axis of this horizontal G1 will be through this point. Then for this web portion will be passing through this point, and for this flange it will be at the exact middle. So all these G1, G2, G3 are passing through the same y axis y, and this is actually y. So IGYY is equal to IG1 YY plus IG2 YY plus IG3 YY. Okay, so we are considering this axis, which I am marking with this arrow. So with respect to this axis, eraser, pointer pen. For this axis y, we have x bar is equal to 60. So x bar is equal to 60. So we located that from this point to this point, the value is 60, and the y bar is equal to 100. It is from this one to this one, because total height is 180 plus 10 plus 10, 200, 100. So we have G1, G2, G3. IGYY is equal to, for the first area, 1 by 12 into B is actually this small bit, 10 into 120 cube plus G2 is base width is 180 into thickness is D is actually 10, and similar for the G3. G1 and G3 are same. So you got this much value. Now, so the centroidal axis of these individual figures is the centroidal axis of the entire cross section. That's the main thing. So you don't want to use the parallel axis theorem for shifting the axis. But for the IG axis, the individual centroidal axis of G1 will pass through this point, G2 will be through this point, and G3 will be this point. Even for this case, the for the G2, okay, we will do that. So Ig excess is equal to Ig1 excess. So individual moment of inertia of this area 1 plus A1 in H1 square plus Ig2 excess into A2, sorry, plus A2 H2 square plus Ig3 excess plus A3 H3 square. H1, H2, H3 are the vertical distances, G1, G2, and G3. So Ig1 excess. So that is shifting the area 1 moment of inertia with respect to the centroidal axis. Okay, to the G. That is 1 by 12 into base BD cube. So 120 into 10 cube. And IG2 is 1 by 12 into base width is 10, 10 into total height 180 cube. Then we have H1 is equal to H3 because taking with respect to the centroid lattice we considered H1 and H3 both are 100 minus 5, that is a total height is 200. So uh, from maybe this is let suppose this is actually 100. Okay, so we have centroid at a distance of 5 from this point. So 100 minus 5, 95. Even the sign changes. I told previously that even a square term is coming, so that the sign doesn't matter for h value. H2 is 0 because the centroid axis of this area 2 is the centroid axis of the entire cross section. So there is no need to use the parallaxis theorem for the second figure. Substituting the values, we get the final moment of inertia. Okay, this I was explaining alternate method for finding the IGX. So this was a one method, and another method is we know that total as this is having symmetry, you can deduct the individual moment of inertia of 2 and 3, which has got same value being symmetric, from the total moment of inertia of the bigger cross section assumed. IGXS is equal to IG1XS, that is full area minus area 2 and area 3, as area 1, 2 and 3 are same 2 times. IG1 minus 2 into the. So B is equal to, so we have to find this small width B is equal to total B minus 10. 10 is the width of this web by 2, and total D, small d is equal to total depth is 200 minus 2 times thickness. Thickness 1 is 10, 10, so 20, and not we don't want to divide it by 2 as only single values, like D is actually total depth minus 2 times the thickness, 20. So BD cube by 12, bigger rectangle minus 2 times the small rectangle moment of inertia. Directly you got the same value 2654, then 4 zeros are coming. So in a simple step you got the moment of inertia on accounting the symmetry. Calculate the moment of inertia of the shaded area shown in figure with respect to centroid axis. So this is the figure, and please note that there is a cutting at the middle. Okay, so calculate the moment of inertia of the shaded area shown in figure with respect to centroid axis. Okay, so the base width of triangle is 60. The altitude is 30 plus 50, 80. And a cut of diameter 50 centimeter. Distance of the given 30 and 30 from both sides. So we are dividing it into two areas. Area 1, full rectangle, sorry, full triangle, and 2 is a circle area. Area 1, half pH, half into 60 into 80, 82 pi r square, circle area. And x1, we know that so we have, there will be individual centroids for triangle G1 and G2, centroid for the semicircle, sorry, circle, and G will be the final or the centroid of the entire section. So x1 is equal to x1 is for the first triangle area. So it is 2/3 of 60. This 2/3 is there because we know that the centroid value with respect to this point, say pointed option, pen, and have drawn a red line. So we know that the centroidal from the this junction or this corner is actually BH by B B by 3 and H by 3 from the this point, right? We are taking the uh, calculating the centroid from this this axis. This is actually the y and this is actually the x. So x1 is equal to 2/3 of 60, right? 60, we know that 60 is this total value. From this point it is h by 3. So from here to here it is remaining 2/3 of 60, 40. x2 x2 is from here to down, directly the uh, total is actually 30 plus 50. Mm, just a minute, sorry. This x2 is actually for the circle, semicircle area. So circle area. So we have total 60. So this point is exactly at the 30 from the left extreme. So directly the x2 is also 30, right? Y1 we're taking from base, so it will be like the previous one, 2/3 of 80. From bottom it is 1/3 of 80, and from sorry, from this base it is 1/3 of 80, and from here it is again 2/3 of 80. Y2 is 50. So we are taking from here. Total depth is 80. So 80 minus 50, sorry, 80 minus this 30 will give you pointer pen. So from this point to this point, it is actually 80 minus 30, 50. So directly x bar is equal to, taking a minus, that we have deduct the circle area from the triangle area. Similarly for y bar, and we got the value s bar, y bar, and then we have to shift the moment of inertia to the new or the centroidal axis of the entire section. So ig axis is equal to ig1 axis plus a1 in s square minus I2 Ig2 xs plus A2 s square. So we are actually shifting the centroid moment of inertia with respect to G1 to G, and directing the centroid moment of inertia of with respect to G2 to G. So we have Ig1 xs plus A1 s square. We'll take the first term first. So it's equal to, we have previously uh, derived that for the triangle we have the moment of inertia uh, with respect to the base given as bh cube by 36 plus 1 by 2 into 60 into 80 is area into distance between the distance between the g and g1. So we have the x1 point. So the centroidal axis, the new central axis is actually this x's and yy. So we are deducting the h as difference between g and g1, which is equal to 0.265 minus pi. Okay, so by substituting this, we'll get the first bracketed value minus pi d raised to 4 by 64 is the moment of inertia of this individual circular area, and that plus pi square D is actually 15 by 2. So this will be the area of the circle into the difference between the centroid axis as of the individual this circle and the total. So this G2 minus G. Okay. So you got the values of IGXs, and similarly you can find for the IGYY by subtracting the uh, moment of inertia of the triangle with respect to the centroid axis. From that, you have to subtract the circular area moment of inertia about the centroid axis of the entire figure. So you can solve in that. Thank you.